Good day and welcome to another exciting class on filters and voltage regulation. I remain Engineer Felix Ezoke and I'll be taking you through this lesson. So today's course is the continuation of the last video that we just did, which is rectification. So this is a continuation, filters and voltage regulation. First of all, what are filters? Filters is an electronic device that converts the pulsating direct current into pure direct current. You remember in the last video, we talked about pulsating DC. DC that has not been completely filtered. So this is what we mean by pulsating DC. And in the last class, or in the last video, we said that the output from a full wave bridge rectifier is a pulsating DC. And we are going to look at see the unidirectional flow of current, direct current. So we are trying to achieve this. So we'll be looking at filters. Filters will help us to do what? To convert this pulsating DC into direct current, into a pure direct current without ripples. And an example of a filter is a capacitor. A capacitor is a filter. So in the quest for regulating or converting AC into DC, we have gone through this stage. We have gone through the transformer stage. Then we have gone to the rectification stage. An example of the rectification stage, an electronic device that does rectification, is the diode. Then the next stage we are in is what? The filter stage. This is the filter. And an example of a filter is what? A capacitor. So this is where we are now, before we now go into the voltage regulation stage, which we'll be talking about. Now, there are different types of filter. We have the capacitor shunt filter. Capacitor shunt filter. What this means is connecting the capacitor in parallel with the rectifier. We also have the inductor series impute filter. As the name implies, it is connected in series with the rectifier. And then we have the LC choke. What L means is inductor. LC, that is the choke impute filter. So under this LC, we have different arrangements. We have the L series and C shunt. L in series and C, which is the capacitor, in shunt. We also have C in shunt and L in series. C, you can shunt the C, that's the connection, and put the L in series. And then we have the pi. So this pi is a combination of the capacitor, the inductor, and the capacitor. That is connecting it in the pi form. Now, what is the shunt capacitor filter? Like the name suggests, the capacitor is shunted or placed across the load impedance. And how do we do that? So still referring from our rectification circuit, where we have the transformer, and then we have our bridge rectifier. Okay. In this manner. So after this, the next thing we are going to be connecting is the capacitor. This is the capacitor. And then this capacitor is the filter. The capacitor, this is the capacitor shunt. This is the capacitor shunt before we can have the load. And the load is the RL. So we have C. So if it's an electrolytic capacitor, you can have it in this form. Okay? So this capacitor, when it is placed across a rectifier, it gets charged, and then it stores the charge energy during the conduction period. And when the rectifier is not conducting, the energy is delivered back to the load. If we remember our output, waveform, where we have the pulsating DC. This is the pulsating DC. And in the last video, I explained the process of the positive half cycle and the negative half cycle and how we got to this point. Now, the capacitor, during the positive half cycle, the capacitor charges. Okay? So we're looking at the waveform. The capacitor will charge. So when the capacitor charges alongside with the positive half cycle, when it's during the negative half cycle, when it's trying to discharge, the capacitor will give out its own stored energy. And then will not allow this to completely come down to zero. So we have a waveform that looks like this. So you can see, so the dotted lines are where the capacitor charges. So at the end of the day, we have the impute waveform to look like this. So the larger the value of the capacitance, the finer the ripple factors would be. Okay? So through this energy storage and delivery process, the time duration during which the current flows through the load resistor gets increased, and the ripple will decrease to a great amount. Now, this is the waveform from the capacitor shunt filter. Now, the next point we are going to talk about is the inductor series impute filter. The inductor L is connected in series between the rectifier circuit and the load. Now, the inductor carries the properties of opposing the charge, or rather the change in current that flows through it. So like the name implies, we want to look at another method. If the capacitor may not be able to do all this, we have to we could connect an inductor. Remember our circuit, or rather symbol for inductor. So we'll connect it in series with our load. And what does it do? The inductor L will block any AC, any alternating current, and allow DC to flow through it. Remember, an inductor is just a piece of wire that is turned. So while it is turned, it allows DC to pass and blocks AC and allows the DC to flow through. So we get a finer output from the inductor with little or less ripple. So we begin to see something like this as the waveform from an inductor series impute filter. The next filter that we are going to be looking at is the inductor capacitor filter. In our first example, we used only a what? A capacitor. In the second example, we used an inductor connected in series. Now, the advantage of the capacitor and the inductor, because the capacitor, its advantage, you use it where you require more output voltage. It gives a greater output voltage when compared to the what? To the impute, or rather series connected inductor filter. Whereas if you want to get more current, or more current expected at the load, you can use the inductor alone. So we want to combine the advantage of the capacitor filter and the inductor filter, and then we have the what? The LC. So the LC will now be having to combine both, which is the inductor and the what? The capacitor connected in shunt before we have the load, which is this. So we have the capacitor here. So you can see this is the LC filter. So this rectifier output, when given to this circuit, the inductor will also allow DC components to pass through, blocking the AC components in the signal. Another name for this is called the choke impute filter. So this is the choke impute filter. And this choke impute filter will give us a higher voltage and current at our load. Okay? Now, the output of this filter is better than the previous ones that we have actually mentioned in the past. So another name for this, like I said, is the choke impute filter. So one can call what? The inductor the choke, because that is the input to it. Now, under this, we could have different arrangements. We could have the capacitor connected before the... So let me just pick the circuit from here. We could have it also in this form. We have the capacitor. And then we'll have the what? The inductor connected, which is the choke. So this is another arrangement where the capacitor is connected. Remember, I said under LC, types of filter. Under LC, we have the capacitor connected in shunt with the inductor in series, or we have the inductor in series and the capacitor connected as the shunt. So to further increase the smoothing action of this filter circuit, just one LC may not be enough. So depending on the output you need, depending on the electronic appliance, some may work with more ripples, less ripples, while some will require pure DC output. So to further filter it, to make sure that there is no ripples that are left, the pi filter or capacitance input filter was developed. So the concept is having the C, L, and then we'll pass another C here. Okay? And so this is the pi. So you can see it looks like the Greek letter pi. Okay, so that is how we have the name. So this is the pi filter, or you can call it the CLC filter. So this filter is divided into two capacitor filter and an L section. So the capacitor C1 does most of the filtering in the circuit, and the remaining ripples is removed by the L section and the filter of C2. So C1 is selected to provide very low reactance to the ripple frequency. So in summary, we have the block diagram, which I said from the transformer stage to the what? To the rectifier stage, and then to the filter stage. We'll be looking at the regulation stage, which is where we make use of regulators. And one fine Or very important diode, which I promised to talk about, was the Zener Diode as a voltage regulator. The Zener Diode is a special diode that allows current to flow in both directions. That is the reverse, the forward or the reverse. The Zener Diode is always operated in either of these conditions, in as such as a simple voltage regulator circuit can be designed using a Zener Diode to maintain constant DC output across the load, in spite of variations in input voltage or changes in the load current. So doing that, because of this property, we can include a Zener Diode when the breakover voltage is achieved. The Zener Diode will now maintain a steady supply of voltage. So if you have a Zener Diode, for example, that is labeled as 5 volts, watch the connection. The connection is connected in an opposite manner. Okay, this is the symbol for the Zener Diode. You have it connected in the reverse bias mode. So once the breakover voltage is achieved, the breakdown causes the output voltage from this circuit to remain constant, irrespective of the output or input current being drawn by the load. That is how we achieve voltage regulation using a Zener Diode. There is also an IC known as the voltage regulator IC, which is also common. We can use it to achieve this. It is labeled as, it looks like this. It is labeled as LS78XXCV, where XX signifies the amount of voltage, that is the voltage you want to be constant outside the what? Outside the circuit. So if we have a voltage, of 7805, this 05 is the voltage we are expecting. So when you see a regulator with this inscription, LS7805CV, pick this number and look at the last 2 digits. That is the value of the permissible voltage that is allowed to flow from the regulator, the voltage regulator. So in other words, if I have 7812, 7809, so this is what I'm looking at for 12 and what? 09. So the output voltage from this voltage regulator is 12 volts, and then from this is what? 9 volts. So with this voltage regulator, having gone, or rather the alternating current, having gone through the transformer stage, the rectifier stage, the filter stage, and then we have looked at different types of filter, okay, whether it's the capacitor, the LC, or the pi, and then we'll finally go through the Zener Diode, which will make sure that we have a smooth DC output, which is a fine line, right, that is unidirectional without any changes in its output. So the connection of this, that is the polarity of this, is in this form. The first leg, when it's facing you, is positive, negative, and positive. So if we are to replace the IC in this form, we will have something like this. This is the IC, 7805, for example. We have this connected as negative. Here is positive, and then we'll have the positive output. Okay, and then we'll have the load. So here we could have a light emitting diode as our load. Okay, remember the symbol, a diode with arrows coming up. So this is the LED. So at the end of the day, this is our output. But with 5 volts flowing through this LED, we would like to use a current limiting resistor, which we are going to connect in series with this LED in order for it not to burn. So maybe we could just use a 1 kilo ohm resistor. Now the job of this is just to limit the current flowing this in order to keep the LED powered on. So when we come to the center for your practicals, we are going to be constructing a power supply that we will finally measure the output voltage and probably see the output waveform through an oscilloscope. Until we meet next time for our next lesson, I remain Engineer Felix Ezoke. Do have a nice day. Thank you very much.